One quick sort of meta comment. So again, please keep telling us what you think in the surveys. I always read them. I love reading them. I try to address them. This week it was kind of hilarious because some people were like, why are we talking so much about Lyapunov? And some people were like, I want more examples of Lyapunov. And they're like almost all interleaved in the random anonymous feedback. So if I don't specifically address your comment, it's because it's hard to address them all at the same time. But I think that's great. We have a diverse background and diverse interests, and that's one of the things I love about the class. Okay, so today, well, let's see, last lecture, I kind of hit you over the top of the head with a bunch of ideas about we're going to use convex optimization to think about Lyapunov, and why Lyapunov, as opposed to optimal control, gives us an opportunity maybe to get farther with convex optimization. So I'm going to start, I'll recap a little bit what we said, some of the key ideas, because I know there were a lot of ideas and details last time. And I think it'll be pretty satisfying when we get to the end of today. You'll see some algorithms that are really useful. Okay? So let's see, last time we were working with the standard sort of Lyapunov conditions, right? So they're variants of the form given a dynamical system, right? We're going to try to find functions that look like this. And one of the first things we did, we talked about if you have a linearly parameterized function approximator, call it a linear neural network. And if you're willing to sample a bunch of states, so I'll say for all xi, okay, where that's a discrete set, then these just become a bunch of linear inequality constraints. Yes? You're right, I did. I said exactly the wrong thing. For all xi, then that's a linear program. Right? Because I can insert xi in here. The nonlinearities of the Lyapunov, the nonlinearities of the dynamics kind of go away because of the sample, and these things are still linear in the parameters, right? If I parameterize this with some vector alpha, and v was linear in alpha, then those things become linear constraints. Okay, so that was sort of our first connection of optimization with Lyapunov, and I think it makes sense. But the big question I tried to sort of get you thinking about last time was, how do we go from samples, for all xi samples, to for all x, really for all x. If you care about certification, guarantees, then the sample points aren't going to get it done. We talked about that in the case of the linear, in the case of the pendulum, right? There was a point where v was 0 somewhere else at the top of the pendulum, and we just didn't sample it, so the algorithm got away without it. Right? If you really care about having a guarantee, then you need for all x. And actually, just in general, sampling scales badly in really high dimensions. And there's cases where the tools we have for all x actually do better in high dimensions because you don't have to sample. And the first example I gave you of that was how it plays out in just linear systems, right? Where we choose always, these quadratic Lyapunov functions. And then the Lyapunov conditions, asking for v of x greater than 0 is equivalent to asking for that matrix to be semi-definite, okay, or definite. And that's just the definition of a positive definite matrix in that case. And then v dot of x, right, we said could be written as we want this thing to be less than 0, which is equivalent to the matrix PA plus A transpose P being negative definite. So by checking now relatively simple conditions on the matrices, there's a big step that happened there, right? I mean, it's easy to take it for granted because it's for linear systems or whatever, but in the linear systems case, just evaluating at the matrices P and PAT gives you says something about for all x. We're leveraging positive definite matrices. So that was our first way of going to for all x. And then the promise is that that's going to generalize to more nonlinear systems. That same intuition. And while the linear neural network case gave us lots of, like at every sample point, we got some linear programming constraints, linear constraints, inequality constraints. Here we have a different type of constraint. This is going to be written as a semi-definite constraint, right? Semi-definite programming, an SDP, right, where we say I'm going to find some P of x, some P greater than 0. And then remember, there was an important trick there. We said that if we have a solver that knows how to handle constraints of this form, and it handles linear constraints, that we can also write constraints of this form. By the way, these are generally called linear matrix inequalities. LMIs. You hear that buzzword, okay. But it's sort of clear because I can say I'm going to make a second matrix, make it greater than 0, which is in the library of things SDP does out of the box, okay. And then I can say I'd like PA plus A transpose P to equal negative P2. And those are linear constraints. I wanted to remind you of those because we're going to do the same kind of thing today. So this is a really important example to sort of understand. Now, Anise, you asked a very good question about we're doubling our number of decision variables. Is that a problem? Yeah. So, I mean, actually, the number of decision variables probably doesn't affect the solvers too much. The number of semi-definite constraints will slow down the solver. That's true, okay? But I actually think for problems of the class we're looking at, these are small constraints, and they should be fine. Okay. Let's think about how to extend that basic recipe to the nonlinear setting. All right, and we can back away from Lyapunov for just a second and just say, if you have a function f of x, it's even say a scalar function. How do you prove it? How do you show is f of x greater than or equal to 0 for all x? The recipe that's sort of suggested by this exercise would be, the generalization of this to nonlinear things would be if I can write this as some nonlinear basis functions times a positive definite matrix, okay? You can do positive semi-definite here. If I could somehow factor my f, then this positive definite matrix, this sort of squared decomposition of this thing is a certificate that it's got to be greater than 0 for all x, right? If p is greater than 0 for all x, that means that for all x, x transpose p of x is greater than or equal to 0. That's the definition of a positive definite matrix. So certainly, this is still just another variable. If it works for all variables, then it must work for this value. That must also be true. And this, you could think of this as like the right, sort of the rich generalization of, if you were to write, for instance, just a bunch of functions squared, okay? This is actually very conservative to say that every one of your basis functions squared, and you're only going to get positive alpha I greater than 0, right? This is sufficient if you are able to find a sum of squares in this form. That would show that f of x is positive. This is just a generalization of that simple idea. Okay, it's the natural generalization. So if you find something like this, then this is called a sum of squares, sums of squares decomposition of the problem. And the matrix P, the real values in that matrix P, are effectively a certificate which tells you that that this thing is positive or non-negative for all x. Yes? So if it comes out of a semi-definite program, and the solver has said P is positive definite, then you don't even have to check the eigenvalues. You trust your solver. Yeah. And you know, solvers are only accurate up to some numerical tolerance. Actually, even eigenvalues are only, you know, the eigenvalue computation are only accurate to some numerical tolerance. If you really want to certify, like absolutely, people do rational arithmetic. They will find rigorous certificates with no floating point errors and things like this. I never do that. Right? It's like, if it's within 1e to the minus 6, I'm good. Right? But it is possible. Yes? That's another point I wanted to make, actually. Right? So I defined a semi-definite programming solver as something that takes constraints of this form. Doing this is so common that many of the semi-definite programming solvers actually just consume this directly, and they can, you know, it's up to their implementation details whether they avoid making that copy or not. Yeah, some of them will just consume that directly. Does that make sense? This is a big idea. We're going to say sum of squares, SOS, a bunch today. Sum of squares, not emergency, the ship is sinking. Sum of squares. Yes? Right, so if you have an eigenvalue that is like 0, then that's where the numerics become a little bit, you know, you have to decide if you're happy with 1e to the minus 6 tolerance, you know, or if you want something better. That's where, and I felt like I distracted, you know, I didn't want to write the like minus epsilon x transpose x. That's a kind of, in some sense, that's a detail, but that's a detail that addresses exactly this kind of concern, right? So if you want to, you know, say I've got tolerance of my solver 1e to the minus 6, then I put epsilon a little bit bigger than that, and you can kind of have more confidence that the solver is giving you an answer that you can trust. I'm going to use, I use the word certificate when I mean a bit like the value function we talked about, or the cost to go function. If I bring you, you know, I don't have to tell you how I got it. I just tell you that here's the value function. It satisfies the Hamilton-Jacobi equations. Therefore, your thing must be optimal as long as it's consistent. In the same way, I don't really have to tell you how I get it, but if I can give you a p that you can check as positive definite, and it matches in equality the original function you cared about, then that's a proof that this thing must be greater than or equal to 0. It's a lot like, it's a generalization of factoring. If you were to give me, and maybe I should even do a couple examples here. I've got one sort of set up. Right, so if I ask you, for instance, you know, is this greater than or equal to 0 for all x then you can just do that by inspection, right? You know that this is greater than 0. This is always going to be greater than 0, right? If I give you a slightly harder one, then that one, by inspection, I can't tell. But if I can write down, and you could factor this into a sum of terms that were all something squared. Right? And that would be a certificate in some sense. The factorization would be a certificate. Okay, and we're going to do, this is effectively exactly that. It's just that my factorization takes this form of a matrix. Matrix form. Good. So this is actually, this is bigger than Lyapunov. It happens to be a particularly nice match for Lyapunov because the gaps that we have, which I'll talk about in a minute, sort of are okay for Lyapunov. They might, if you can find a certificate, then you have a guarantee that the system is positive. There are systems that you might not be able to find a certificate. The reverse logic is not true. Let me say that again in a second. But this becomes like super powerful in the case of polynomials, let's say. I'll just call it little p polynomial of x. So this could be a multivariable polynomial, but in a single variable polynomial, just imagine right, alpha are my coefficients. So this is a linear function of the nonlinear basis functions, which are 1x, x squared. If I want to prove that some polynomial is always greater than 0, then I can factor that into this big P of x. Okay. So to make this statement work, there's kind of two things I need, right? The first thing I need is I need an STP solver that can handle this kind of a constraint. The second thing I need to do is to be able to equate, maybe there's three things I need to do. I need to be able to pick a basis function, a set of basis functions, phi, okay? And then I need to be able to make this left-hand side equal this right-hand side in a tractable way. Okay? So you can imagine if I have a polynomial that can be written, for instance, as a linear function of 1x, x squared, okay, then there's a natural choice of what my basis functions need to be here on the right-hand side. In fact, I can choose phi of x just to be, in this case, I could just choose it to be 1x. And I know that this thing, when multiplied out, is going to have terms that correspond to 1, correspond to x, and correspond to x squared. Okay, and the simplest choice of basis functions would be a monomial basis. Sometimes we'll write mx for a monomial basis. Which is just all of the, this is a polynomial. The monomials are things that are the variables raised to some power, okay, but no sum. So if I just make a monomial basis, which would be all of my 1x, let's say y, xy, x squared, y squared. You give me a multivariable polynomial, I can write a monomial basis up to some degree. And the maximum degree in this the degree of this polynomial, the square root of that degree is going to be, the ceiling of the square root is going to be a sufficient degree for my monomial basis to know that I can get all those terms. Okay? So in order to say I've got some function, it's equal to a quadratic form, I just need to know what a basis function. And in polynomials, I know the basis functions. They're easy. I just know they're going to be the monomials, for instance. You can do better. You can have more efficient bases than that. Okay, but that's certainly a sufficient one. Another thing I need is to be able to write constraints that say that this right-hand side equals, this left-hand side equals this right-hand side. Okay, P here is our, this right-hand side is linear in P. All of the terms are linear in P. And this side, so if I want to make this side equal to this side, that's a bunch of linear constraints on the coefficients here to match this. So it fits beautifully in semi-definite programming, right? So if I have that 2 minus 4x whatever, then I could say 2 minus 4x plus 5x squared. Let me write that instead as 1x p, but maybe I'll even write it out. I'll just make a big matrix here. P11, P12. These are symmetric matrices, so I get 1, 2 again here. P22. There's only 3 decision variables on this side here. 1x. So I can write an optimization that says I want to find a p greater than or equal to 0, and I have a constraint that the terms that multiply through here that are going to be coefficient of 1, that's going to be just P11, that has to equal 2 for me to match my left-hand side. Okay, I have 2 times P12 is going to be my linear term. That had better equal -4. Okay, and then P22 is better equal 5 if that's going to match. So if that matrix, which is actually fully defined in this simple case, is positive definite, then that thing must be greater than or equal to 0 for all x. Okay, but the essential thing is that the ingredients, when you have a polynomial, okay, all the ingredients you need are compatible with semi-definite programming. You need to be able to write a constraint like this, and you need to be able to write a bunch of linear constraints, and that's exactly the specification that semi-definite programming provides. This one? That's intentional. It's just it's a symmetric matrix because I want it to be positive definite, so I can actually define it to be symmetric. Yeah? If I make a bigger problem, it wouldn't be that. I thought about writing it out. If I read it out, even if I just checked my basis wrong, I did 1x plus x and x squared here, then they would not be fully defined. I'd have some linear equations here. Yep. Yep. This is just because I have the same number of coefficients as I have decision variables here. Yes? It's only the other way around. If I say semi-definite, positive semi-definite matrix, that by convention that implies that it's a symmetric matrix. Like if I say PSD, it's symmetric, right? Because you can take any, there's always a symmetrization of any matrix that is always positive into a symmetric form. So by convention, we just say that it's, when I say PSD, I mean symmetric. The opposite is not true. Not every symmetric matrix is positive definite. Okay, so for an arbitrary function, if you can find some basis functions and you can find a p, then you have a proof that this thing is a sum of squares. That implies that it's a positive for all x. In the special case of polynomials, it's relatively easy to do that because the basis functions are clear, okay? And the coefficient, the matching that equality is just matching the coefficients. That's the only thing that's special about polynomials. There are other classes of functions that could be special too, but polynomials are actually enough for us to do most of the robot things we want, and we just understand them a lot better. Yes? Yep. You got it. That's true. So we can do it. So, yeah, the punchline is that actually robot dynamics are polynomial, but they're polynomial in cosine theta, sine theta. And the important observation there is that you'll never get like cosine inside the parentheses L theta or something like this. Actually, it's always cosine theta. And so you can actually just take that out and call it C, and then you're polynomial in that. And the reason that's got to be true is because rigid body mechanics is exactly saying that distance is preserved, and Euclidean distance is polynomial constraints. We tend to write them down with trigonometrics, but it's all polynomial. Okay? Yes? That's today's context. But this is useful beyond, right? I'm giving you a tool for life. And we're just using it today for Lyapunov. Yeah.
So if we find a P that's not positive definite, can we then always say that so this won't hold in general, or could it be that we get that transformation?
That's a great question. So the question is, what if let me say we find something that's an equality basically, but basically we could not find a positive definite matrix that makes that equality. So the reverse implication is not true. If you find, even in this form, if you find this side and you match an equality, then that implies that this must be positive for all x. But there are functions that are positive for all x that don't admit a sums of squares parameterization. So the reverse implication, this is why I kind of say it's great for verification, for Lyapunov. Once you find it, you do have a guarantee. But you cannot guarantee you will find it. Now, this is where the mind the gap joke happened on accident last time. So you have to work, so like theory people find problems where this is positive and you can't find a sums of squares decomposition, but you have to work you get a thesis out of it if you find one, right? It's in practice, okay, well, actually we know a lot, so sorry, I should be more careful. Like in the univariate case, there is no gap, okay? This is Hilbert's problem, actually. There's a few special cases where we know that there's no gap, okay? As the dimensionality goes to infinity, then the gap gets big, okay? But there's actually a lot to know about this. This falls into the land of algebraic geometry, and there's like beautiful math underlying all this stuff. For robots, roughly a meter long, that have degrees of freedom between 1 and 100. Don't worry about the gap. That's my rough advice. I don't think the meter long matters. That was just a habit. Okay, awesome. This tool for life is so powerful that we sort of abstract it. Okay, so the same way I said that semi-definite programming was something that took a linear objective plus linear constraints plus PSD constraints, if you will. That was our definition of semi-definite programming. This is the kind of things you can hand to the solver if someone claims to have a STP solver. There's something called sums of squares optimization, which is a generalization of SDP, which does all these things, but also allows you to pass in something like this. Constraints of the form, I'm going to give you a polynomial, and you can constrain that it is sums of squares. And under the hood, it actually calls the SDP solver. The solver doesn't have to know about it. This is typically a pre-processing. Like in Drake, mathematical program does this for you. And the solver just knows about semi-definite programs. But it will it'll figure out the right basis functions for you. It'll generate these decision variables for you. It'll register this constraint. And it'll find all the linear constraints to do the coefficient matching. And under the hood, it's an SDP. Okay, but one level up, we get to start writing programs where you just say, I want this function to be a sum of squares, which implies, if it's satisfied, that implies that for all x, for all x in Rn, P alpha x greater than or equal to 0. This is how we get around sampling x. This is the magic. Sums of squares. Yeah? Thumbs up, thumbs down in the middle. Okay, good. It's super powerful, like beyond Lyapunov. And it does things that you kind of think, I didn't think convex optimization could do that, right? So you asked the last time, you said, so isn't convex optimization kind of limited? I think the people who are really good at convex optimization don't see those limits, right? I think there's, well, okay, the trivial statement is that everything's convex if you go to high enough dimensions, but that's not useful. But I think in useful dimensions, you can often find very convex convex relaxations of a problem that are very close to the original problem. So solving the convex problem can actually give you answers to the original one. Here's an example, a sort of famous example. A 6-hump camel. Sounds very funny when I read it there, but it's the name of the polynomial, okay? It's a polynomial in 2 variables. I'll write it quickly just because it's so easy that it's worth writing, but just it's an arbitrary, you don't have to write it down, right? It's just an arbitrary polynomial, famous polynomial. Okay, and if you plot it, it's sort of convincingly non-convex. It's kind of, it's like got local minima all over the place. Okay, and so, geez, if you want to formulate an optimization problem that tries to find the minimum of this non-convex function, you'd think convex optimization is not going to help me with that, is it? Enter sums of squares. Sums of squares has an answer to that. I'm going to try my version of this, see if it helps. Let me make this way bigger. Okay, I'm basically going to call a mathematical program. I'm going to register my decision variable. I'll tell you more about that in a second, but basically going to say P of x, I typed it in here, okay. Add a sums of squares constraint. What am I going to write if I want to optimize this? I'm going to write this as a sum of squares problem saying I want to minimize over gamma minus gamma subject to P of xy minus gamma is a sums of squares. Okay, so I want to find the lowest value of that function by finding the smallest gamma, that if I were to shift the function, it'll be positive everywhere. It's, apart from declaring the variables, it's basically, it's one constraint, add SOS constraint, and then you add a cost, okay? And I sampled a bunch all over the place. It's 2-dimensional, so I could just solve it brute force, okay? And I showed the SOS solution, and it finds the optimal solution, okay? Cool, right? It does something that you wouldn't think a non-convex, you would be able to do with convex optimization for a non-convex problem, okay?
The nature of solving an optimization problem with the SOS. So we're saying that landscape is better than that.
Correct. Correct. Yes. That's brilliant. Yes. So we're not going downhill in x and y. We've reformulated the problem. Yeah. What are the decision variables here? One decision variable is gamma, but that one's not the consequential one. The P2, if you will, that we used on the other side to make this thing sums of squares, those are the meaningful decision variables. We're walking downhill trying to factorize this equation, right? And in that space, the problem is good again, is convex. And it's a relaxation exactly because of the implication question that you asked. The fact that knowing it's a sums of squares factorization does not implies positivity, but the opposite is not true. That opposite is not true case means there could have been some other function that was positive everywhere, that was tighter on this original function, that just wasn't a sums of squares. That's why there could be a gap between what you get out of sums of squares and what the true optimum. But if that gap is small, if sums of squares is strong enough, then the problem is roughly solved. Did I say that well enough? There could be a function that lower bounds this, which is positive everywhere, but is not a sums of squares. We're going to find the best sums of squares that satisfies this. And in this case, it's tight, and in many cases, it's tight. Yeah? Right. So, yeah, there's a cool picture that people draw of the semi-definite cone for 3 variables, right? So for a 2x2 matrix, you can do it, but this one's all the way up to degree 6 and stuff like this, so it's hard to draw that. Right? You can do the standard things people do with neural networks. You could start staking slices and look at it in every plane or whatever. So you could, every slice should give you something that's convex. Yeah.
How do you know how big
So this is again. So you could check afterwards. First of all, you could check the value, right? But going in. The reason that it's such a good match for Lyapunov is that there are many Lyapunov functions that can certify a program. So it doesn't have to be perfect. This gap doesn't kill you, right? So that's why I'm advocating it and teaching it in the language of Lyapunov. That's where it's seen the most success. That gap doesn't hurt you.
So this is all you have to shift that function outside 1.03 in order for it to be positive.
Yep, you got it. That's exactly right. This actually, if you notice, the decision variable here is not the xy value. It's not the minimizer. It's the minimum. It's the value that is obtained at the minimum. So out of the box, you have to do a little work to dig out the minimizer. You can do that by looking at the dual of the optimization, but that's more than I was going to get into today. There's a dual program where the decision variables are the minimizer. Okay, so does it only work for polynomials, right? Again, the concept of the sums of squares is general. The utility of using semi-definite programs is it's not only for polynomials, but it's particularly powerful in polynomials because of you get these PSD constraints and you get linear equality matching. Even if I were to start putting sines and cosines here, the term matching, that's what they call it, right? Saying that everything on this side matches this side. You can do it directly in trigonometric variables, but then you have to write a term matcher that handles all of the trig identities, for instance, right? To make sure that the right-hand side equals the left-hand side, you got to get the cosine plus whatever. It just gets more complicated. It's possible, okay? And then the theory about all the gaps and what happens in high dimensions and all this is just much more developed for polynomials. So that's why. And it turns out robots are polynomials. It's kind of interesting to think about what this would be for a neural network case. People don't think polynomials are cool anymore, but neural networks are cool. So what would it, if you wanted to say, prove f of x greater than 0, for all x with a neural network, you could choose maybe f of x equals, can I say neural network of x? But maybe I'll take transpose times another neural network of x. This is the kind of thing people do to guarantee positivity, right? And then the question would be, how do you do the equation matching? If you have something that's like, you know, my Lyapunov candidate and my dynamics, which was given to me by physics, right? It doesn't necessarily have the term matching. You could make this sort of like approximate. You could do supervised learning to try to make that, you know, approximately match, and do gradient descent of the parameters of the neural network. That's kind of, that's the way it would connect to neural networks, right? You could imagine, instead of just saying my function is the output of the neural network, I'm going to say the output of the neural network will get squared before it becomes my function, and I'm going to try to make this match up as close as possible with the least squares objective. So you design a class of functions that are guaranteed to be positive, and then make it as close as possible to your function. Okay, tool for life. And when you're talking to your like math friends about algebraic geometry, you'd be like, oh, that's relevant in robotics. That makes them very happy. Let's get back to the Lyapunov case, right? So for Lyapunov, we're working, we'll stick ourselves, or keep ourselves in the polynomial space for now, right? So we get to choose v of x to be polynomial. That's a choice. And then let's assume that our dynamics are polynomial, or restricted, let's say. I will only consider nonlinear dynamical systems that can be written as polynomial equations for a moment, okay? The cool thing is that v dot then, you know, polynomials are closed under this composition, right? So they're closed under the gradient. That's the gradient of a polynomial with respect to the x is still a polynomial, okay? And this was a polynomial. The multiplication of two polynomials is still a polynomial. So this is still okay. So the Lyapunov conditions that we originally wrote with math here are going to be converted into a statement to the solver saying, find me a v that is sums of squares. And similarly, I'll say v dot of x less than 0. I'll say negative v dot of x is a sum of squares. So there's a couple like famous simple examples that are like polynomial dynamical systems that have polynomial Lyapunov functions. Okay, so this is an example. Just take a two-dimensional system. I've got one here. Oop, minus maybe, minus. Okay, just some known polynomial differential equation, and it just happens that it's also known that the Lyapunov function of the form like this is a Lyapunov function for that system. And the real question, I mean, this one is clearly positive by inspection. The question is, can I prove that v dot is actually greater than 0 or less than 0, right? Everywhere. I could sit there trying to factor the polynomial. I'm not going to do that. I'm going to just ask the solver to do that for me. Right, so here's my dynamics, my Lyapunov function. I can figure out v dot by just saying take the Jacobian. So v, Drake has a symbolic library behind it. So when you get x as a out of mathematical program, it's actually a symbolic variable. So you can do things like take a symbolic partial derivative with the Jacobian method, and then I multiply that by this value of f here. Okay, and I just say add a sums of squares constraint. I want v dot to be negative. Okay, and if that succeeds, then I've actually got a proof that that system is actually stable. Right? And it is. Successfully verified Lyapunov candidate. Even though the vector field's kind of crazy, right? That simple Lyapunov function is true, is a certification of global stability. Yeah?
In the first class, when we started discussing finding function, we discussed about this parameterized approach of
Yes.
creating a nonlinear basis.
Yes.
So here we are just saying that our basis is just this continuous, like it's all possible polynomials.
It's not all, well, so it's all, we're parameterizing polynomials. Okay, so I did a simpler case here where the polynomial, where the Lyapunov function was known, and I just had to verify it. So the decision variables in this, that's actually a good exercise. Like, what is the decision variables in that program? The only decision variables were the, you know, were these, right? It ended up writing this for me. And these were the decision variables. Yeah, so let me, I just finished. So it's more interesting, what if I were to replace this with, I don't know what the Lyapunov function is, right? But I'm going to say it's a polynomial of the form alpha 1 x, alpha 2, or x1, x2, plus, you know, alpha 3, x1, x2, so on and so forth. And the question is, can I search over those polynomials too? And if you thought about that in the equation matching, if I say now this is alpha times some other basis, making p, you know, this side match this side, it's still linear constraints in alpha. So I can actually search over the coefficients of the Lyapunov function too. That's what you're asking, right? Yeah. Yes, exactly. So let me, and searching for a Lyapunov function right there, see? So exactly the same thing, but I just said v is an arbitrarily sums of squares polynomial with all terms up to degree 2. That's what the that incantation means, okay? So I just basically had a Lyapunov candidate that was this exactly, okay? And the solution it found was this. So it found the thing that we already knew. And maybe we even knew it. Like, it's kind of circular because the paper that introduced it was introducing sums of squares. So he might have actually called the solver and then just like rounded it off and said no, and then checked the math, and then we're all good, you know. So, I don't know which came first, the chicken or the egg. But that's a nice solution to that problem. Yes. Yeah, so good, thank you. So there's multiple methods in Drake. One of them would be make a polynomial of all terms degree whatever. When you call new sauce polynomial, that creates the polynomial and adds the constraint, add sauce constraint, that polynomial is greater than 0. I was like, geez, did I forget that? No, it's there, yeah. You guys are good. You're good. That's like next page. I promise that. Regions of attraction, next page. Okay? Yes?
What are the characteristics of the dynamics that actually allow this to work? Like, should there be a red flag in the dynamics that are like thinking that something like this is not going to work?
I mean, if the dynamics are polynomial and or nicely approximated by a polynomial, then you have a reasonable chance of this working. There's a lot known, so there's like a lot of math behind all these results. I'm giving you the user's perspective here, okay? So it is not the case that every stable polynomial system has a polynomial Lyapunov function that proves it. Forget about SOS polynomial. It's just like one more gap. It could be that there's a stable polynomial system. You can't prove its stability with a polynomial Lyapunov function. That's a bummer. But again, it's like you have to work hard to find them. In practice, you know, all the robots I've thrown in here, if they're stable, I've been able to find a, you know, proof by trust. Trust me. It's, yeah.
Can you generate like a candidate polynomial that has all possible terms?
Yes.
That has the SOS constraint. One of them clearly is confirming V of 0 is 0.
Good. The other one is just saying V of 1 is 1. V of 1, 0 is 1. That's just a set of scaling. It's just, it's like I said, because you could multiply any Lyapunov functions and get the same thing. It does actually make the numerics better, because if you didn't put that in, then it would try to find a V that was very close to 0, and the solver is going to start fighting its tolerances or whatever. So it helps to just sort of say, I want one that kind of yay tall. Mathematically, it's not necessary. Numerically, it's helpful. Yeah. And mathematically, it's more beautiful to me because it feels like I'm fully specifying the problem. I'm not leaving the solver some undescribed manifold. Yes? It almost made sense. Try one more time. Yes. I think that's true. If I take the output of the second program and put it back into the first program to just verify, it should work. Right? Is that the question? I mean, and similarly, anything that I put into the first program that, and maybe that's the one you're asking is the other direction, is that if I had found a polynomial Lyapunov function, as long as it's a sum of squares, so that maybe there's a little gap there, right? So it could be that you could find a polynomial Lyapunov function that is positive everywhere, that is not a sum of squares. But again, that's one of the small gaps. Yes? Yeah.
So if you can write like if X is as a sum of squares, does that mean V of X is positive or positive?
Sums of squares means positive semi-definite. And then you can do, again, the same kind of things. You could say, is it greater than, or, is the polynomial minus epsilon x squared would give you strict, the same game we played for the linear program, we could play for this sums of squares if you wanted strict positivity. Nice, okay. Regions of attraction. So now you're in the mindset, I hope, of a kind of someone who's got this tool of sums of squares optimization. Okay, and sums of squares optimization, if we ignore the gaps, okay, but let's treat it for now as an oracle. Like the oracle at Delphi, right? Like it's an oracle. I get to take questions of a certain form to my oracle. I say, I have a polynomial function. Is it true? Is it greater than or equal to 0 for all x? That's the only type of question you get to ask the oracle. It's a great oracle. It'll say yes or no. Okay. Now I have a different question. I have a question: Is x positive in some region? like a game, right? It's like an interview question, right? What question should you ask the oracle who only knows how to answer for all x? So that she tells you the right answer for just for x. Okay, that's the question, right? You have an oracle, answers true or false for questions of the form for all x in Rn is p of x greater than or equal to 0. But you have a new question. Let's say in the simple case, I've already picked a ball or something. I want to just prove that the thing is sums of squares, but only in some domain, right? And I'll say it's less than Rn, okay? How do you ask, what question do you pose to the oracle? Yeah.
Like, could you modify QX so that it's definitely larger than 0 for the regions that you don't care about?
That's exactly right.
But preferably in a way where it's still differentiable.
Differentiable. Yeah, the polynomial limitation's got to keep things mostly differentiable and everything's good. Yes, that's the trick, right? Is to come up with a modification of p of x that is trivially positive outside the region, but you haven't changed the question inside the region. That's why he says you want it to be differentiable. So you can't you could have it like be 0 inside the region, and then you add a big positive number outside the region, but that's not differentiable. We want a polynomial function that makes it easier to answer the question outside and doesn't make it easier inside. Okay, so let's do that. So first, let's define D as with polynomials, okay? Okay, these are going to be polys too. I guess I should have said the oracle is even special because it gets to optimize. You can have some free variables when you ask the oracle. And we're going to exploit that too, right? Here's the game, right? I'm going to say, find me an alpha such that p of x, which didn't even have any alphas in it yet, okay? That's the question you ask the alpha, the oracle. Okay, so let's think about it. So this thing here is called, it's a lot like a Lagrange multiplier, if you know constraint optimization, right? This is a multiplier polynomial. So you'll parameterize it as, you have to pick it a priori, you have to parameterize it. Okay, but you put in some, unfortunately, finite, that's going to be a limitation of this approach, some finite parameterized polynomial. And what happens here? So let's just think about the game here. So if g of x is less than 0, and this new polynomial is guaranteed to be positive everywhere, then inside that region, when g of x is less than 0, this thing here is either 0 or negative. It can't make it easier to prove SOS. So certainly inside the region, adding this is just adding something potentially negative. It can't make it easier. So you still have that certificate. If this thing passes, then certainly p of x inside that region passes. Yeah? The other thing to think about is that when g of x is outside the region, then this thing is positive, this thing is positive, so you're allowed to contribute terms that make things more positive. Right? So if I have some region of interest, let's just say I have some region of interest here, okay, and maybe I have a function that is negative below, but is everywhere positive above, okay, I'm allowed to add in some function that's like very positive outside the region, which can fight these terms that were negative. Okay, and it's going to try to be as close to 0 inside the region as possible so that it doesn't make any of those negative. If it was discontinuous, it could do that perfectly, but it's smooth. So it's going to do as tight as possible. Okay, but the implication is still good. If you find this, then P of x is definitely greater than 0 inside the region. Right? Cool. So that's yet another gap because you have to pick some finite. If you were to allow this to go to infinite order or infinite degree, then there would be that would be a fine certificate. It could be arbitrarily, like this, like the indicator function. Okay, but since you have to pick a truncated degree, then there is yet another reason why your function could have been positive, but it couldn't be proved with this method. Okay, that's a really important tool. It's called the S procedure. We don't really know why. I asked Sasha Magretsky, who knows everything about these things, and he said, it definitely came from the Russian literature, but we don't even have the letter S in the Russian alphabet, so I don't know. That's roughly what he said. Don't quote me on that, but that's roughly approximately what he said. Yeah, it's connected to a lot of deep things in semi-algebraic geometry. Okay, so positive null stats is the name, but it's well known. In the simple case, if this were to be just a scalar, then it really is just like a Lagrange multiplier. If you've seen Lagrange multipliers before, this is a generalization where you have a whole polynomial as your multiplier. Okay, and this becomes, like, again, a super useful building block for writing optimization problems. We can write implications of the form. So I will write things like, on the board saying like g of x less than or equal to 0 implies that p of x is greater than or equal to 0. It's just like a kind of a summary of what we've proven here is that when I'm inside this region, then that thing is greater than 0. So like a shorthand. I think of g of x as being given to you by the problem, and lambda of x being the thing you're choosing to find a certificate. Yeah, in practice, so here's an annoying thing, is that the numerics of like taking things to a high power aren't great. And semi-definite programs, you can get, if you start getting to very high degree polynomials, then you'll get more numerical issues. Yeah. So it works best when these degrees are low, and we'll see lots of examples where that's actually very powerful. Okay, it happens, maybe if it's useful to know, if your D was defined as an equality constraint instead of an inequality constraint, then we have even more tools. Like so polynomial inequalities is the stuff of semi-algebraic geometry. Polynomial equalities is algebraic geometry, and we know a lot more. We have like a lot more math. And this will happen. We'll see lots of examples where we can use this form. And the way you would do it in this case is you find me an alpha so that p of x lambda alpha x of t g of x is sauce. And that's it. Lambda can be anything. It can be arbitrary. It doesn't have to be sums of squares. You You don't have to write the second constraint. Why? Because when g of x equals 0, this thing cannot help you be sums of squares. Right? When g of x is 0, that doesn't help, but whenever g of x is not 0, you're allowed to contribute arbitrary positive things to make it more 0. So this is what we needed to do regions of attraction. Okay, g of x less than 0, we're going to say the sub-level set of a Lyapunov function. Right? We want the Lyapunov conditions to hold over the sub-level set of a Lyapunov function. That's what gave us our regions of attraction before we were computing anything, just when we were writing it on the board. So regions of attraction using SOS and the S procedure. Imagine I have, I'll just do the same thing I did before. I did the verifying a candidate Lyapunov function, then we could try to search for Lyapunov functions. It's just easier to think about the case where you're just verifying a candidate. Remember the example I did, which was negative x plus x cubed. That's my favorite simple polynomial, right? Like that. And we knew that v of x equals x squared was sufficient to prove that the region of attraction was inside this. I did that on the board. So what we could write, for instance, is find me an alpha such that negative v dot of x plus lambda of x 1 minus v of x is SOS. Why this? This is saying that v of x less than or equal than 1, which I know to be the region of attraction. And I also need, since this is an inequality constraint, I need lambda x is SOS. Okay? That's the simplest formulation. It's not actually the best formulation. Because when I go then to try to, if I want to optimize V, for instance, I started running to challenges. Even if I wanted to find the region of attraction, I knew it was 1 here. What if I said I wanted to find me a row, right? What if I said find me lambda and a row such that negative v dot of x plus lambda alpha x rho minus v of x is SOS. That would be useful now, because that would find me the biggest level set, or find me a level set, and I can put an objective function to make it find the biggest one, maybe like maximize. Right? But be careful, because I have decision variables here, and if I make P also rho a decision variable too, this is not convex. Because I'm multiplying 2 decision variables together. That's a standard bilinear thing which breaks convexity. So there's a slightly different way to write this that can make that convex. And you will work through it on your problem set. But this becomes, yeah, go for it.
Do you always need to formulate g of x in terms of the Lyapunov function, or can you formulate it in terms of just like the region you're interested in?
So that's why we tried to cover it some detail, sort of you want to be able to prove things over an invariant set. A natural choice for a set that you know is invariant is a sublevel set of a Lyapunov function. So all the things we talked about in the first lecture about the Lyapunov conditions over a region are still held here. There are cases where you can make an argument that some set is invariant and V dot is inside it. Maybe you can choose conservatively. V dot's inside some big region, and I know that there's an invariant set inside it. That could separate it. I understand the reason for your question is you want to break that out and not be a function of V. Yeah, to avoid any bilinearities there. There are cases where you can make that argument, but this is actually the more general, the more common case. Not out of naivety, out of utility. Yes?
So if the algorithm
That's true. And that the region is invariant. Yep, because of that. Mm-hmm. I have the code you could play with, but I'll let you play with that yourself. But just, if we put all the stuff we're doing together, you're starting to get a lot of really powerful tools. Okay, I'll do it with a cubic polynomial example just to tell you, but what if you want to do robustness analysis for the simplest possible function? Right? Let's say just say there's a couple different ways you could be robust in a nonlinear system, but you have to have some parameterized uncertainty, right? So in this case, I said, well, maybe there's a coefficient here, and I didn't know its magnitude. I just put some bounds on its magnitude. Okay, so if you think about like different instantiations of alpha, if alpha's 1, you get the black curve that we always think about, but you pick different alphas, it's going to do different things to the function. So the robust region of attraction is going to be the set for which, in the worst case alpha, I'm still guaranteed to go to the origin. And you can formulate that exactly with these tools by saying for all x, my Lyapunov function has to be for all x and for all delta. And I'll use the S procedure to limit delta and the S procedure to limit x. Okay, I'm only giving you the sort of, the high-level idea right here, but you can just start putting these tools together, and you've got this composition of powerful specifications that you can start talking about, nonlinear systems, regions of attraction, and even robustness. Okay? This is just like when we did for the linear systems. It's a common Lyapunov function that would be called. So say one function that proves the same Lyapunov function that proves for all of those systems, if you will. If I say every instantiation of delta is a different system, I'm still asking it to find one function that proves for all. Again, there's a gap, but in this system, it's great, it's tight. And it's useful. This is what people do for robust analysis, okay? If you had additive uncertainty, okay, which is actually less common. It's very common that your system might have additive uncertainty. It's less common in the papers because it's less convenient to deal with. Why? Like, what does that function do if you just start adding random constants at the end of it? Right? It bounces up and down. So where's the fixed point? How am I going to talk about stability to a fixed point? If you ask for a Lyapunov function that proves exponential stability to the origin, you're going to be out of luck. It's going to say no. If you just ask for invariance of a set, though, then you can get a yes. So if you use all these Lyapunov conditions properly, and you choose less than or equal to when you need to, and choose whatever, then you can say, find me the largest invariant set. And that, it doesn't tell me I'm going to converge, right? Because I'm not. Depending on this, I don't know where I'm going to converge. But it does tell me that if I start inside this region, I'll stay inside that region. And that can still be a very useful quantity if you don't want your car to crash. Right? Airplane. I guess I found out everybody's in aerospace because people are like, I would do spot if I can add wings to it, or or if I could send it into orbit, or if I could, So that's good. Okay, so it's a powerful toolbox. Lots of permutations of the ideas, but the basic ideas I think we tried to cover. I would say also, I can't possibly cover all of the, lecture's not the right format to cover all the different permutations. So please, like, read the notes and like work through some of the notebooks. They're there, they're, you know, tried to be curated. Okay, here's the one you're gonna do on your problem set because it's the best. It's like so good. Okay, so this is a famous oscillator equation. It's called the van der Pol oscillator. It happens to be a polynomial equation, check, right? And it has this beautiful, beautiful vector field, okay? So the black is a stable limit cycle. We'll talk about that, but basically all orbits except for at the origin, okay? If you start at 0, 0, you'll stay at 0, 0. But if you start anywhere else, you'll follow those red lines. This is the phase portrait, right? And you'll eventually be going around the black line, arbitrarily close, right? So how are we going to do a region of attraction analysis on that? Okay, the trick is we're not going to do it on that system. We're going to take that system and we're going to play it backwards in time. So you're going to look at the time-reversed van der Pol oscillator. Dynamical systems are cool. You time reverse and you just kind of flip the vector field backwards, okay? So what happens in the time reverse system? All of the things that were spiraling out to here now become attractive to the origin, and the ones that were coming in from the outside to the origin are going to blow up to the outside. Why is it awesome? Now it's an interesting, simple polynomial system that has a very non-trivial region of attraction, but it's one we kind of know. We only know it numerically, but you can simulate forward, figure out exactly that region of attraction, those black lines, and when you time reverse it, I know that the fixed point is stable, and the boundary of the region of attraction is defined by that black line. So it's a great problem, okay? Now the question is, can I prove it? Like, everything we've done here has been in the effort of being conservative. Like, so if you find a proof, you know it's true. So what we expect to find is an inner approximation of the region of attraction, right? We're only going to certify things that are true, unless we have numerical errors or something, okay? But we might not be able to certify the entire region of attraction. So what you'll see is things like this, okay? So if you take a quartic, I think, like a polynomial of degree 4, you maximize the region of attraction with the types of the details I've got in the notes here, okay? You can like push out on the region of attraction. You don't quite get the whole thing, but you get a big, nice, beautiful region. Okay, you're not going to do quite that well. I think in the problem set we're going to have you do quadratic, okay? And so you'll get something smaller than that, but you're going to see that you're doing the best possible quadratic. Then here's one more system that's kind of fun. So this is just by construction, a problem that is defined to have a region of attraction that is a funny shape. We call it star, okay? The star problem. So that's it's a simple polynomial function, but it just has an interesting ROA, okay? The yellow is a region of attraction that was obtained by sums of squares that is certified and all these things, okay? And it's not quite the entire orange region, but it's pretty big. And it's not convex. That's the reason I like this example, right? So we're convex in this high-dimensional SDP space. But that does not mean we are restricting ourselves to searching over sub-level sets that are somehow convex in X. Those are just different ideas, right? So you can actually find regions that are, not convex in the original space. Typically, the thing we push out on is some metric of volume. So this inner circle is actually the largest contained ellipse, which I know how to compute a volume of, or even that, it's an approximate, okay? And we push out on the volume. The objective function is to push out the volume of that gray region, subject to the constraint that the gray region is perfectly inside the yellow region, and the yellow region is inside the orange region. It gets a little complicated, I fully admit, okay? But the tools are exactly what we just talked about. a sufficient composition of these arguments lets you do really good things. Okay? Even on like bigger systems, right? So since you guys are all aero, right, here's a quadrotor, right? So this is a LQR stabilizing a quadrotor. And you can ask about, this is just to say, it proves a big region of attraction for the LQR controller. The only point of this, like, it's hard to think about those units or whatever, but they're not too tiny. It proves a big, like 0.1 radians is actually pretty big, right? And there's two circles there. And this time it's because there's one where I didn't know the inertia of the quadrotor, and there's another one where I did know it. And when the inertia was uncertain, then you get a more conservative approximation, okay? But you can still get a certificate that things are going to work, as long as your model's right. I mean, up to the uncertain model's right. Okay, good. There's a ton of variations and extensions, and I will just leave those to the notes. Cool. See you next time.